Welcome to the Deep Dive, where we plunge into groundbreaking research to unearth the most important insights for you, fast. Today, we're tackling a really interesting paradox right at the heart of AI development. Our AI systems are just rocketing forward, advancing like crazy, but the actual human research process building them, it feels, well, surprisingly slow sometimes. It's almost like having this incredible hypercar just stuck in traffic.
Exactly.
Yeah.
And that creates a real bottleneck, doesn't it? A major constraint on innovation. But our sources today, particularly this fascinating paper called ASI-ARCH AlphaGo Moment for Model Architecture Discovery, they present a truly transformative vision, a way to potentially shatter that constraint. They introduce something called ASI-ARCH. It's Artificial Superintelligence for AI research.
Okay, ASI-ARCH. And for you, the AI researchers and ML engineers listening, here's the bombshell. This is the quick 1-minute summary of why this paper is, frankly, a potential game changer. ASI-ARCH is the very first fully autonomous system designed for end-to-end scientific research, specifically in neural architecture discovery. Now, this isn't just like a faster way to find AI models we already kind of know about. It's more like AI teaching itself to invent, pushing beyond human intuition to find blueprints for intelligence we maybe haven't even conceived of yet. It goes way beyond traditional neural architecture search, NAS, because it lets the AI autonomously hypothesize, then implement, train, and validate truly novel architectures.
Yeah, the scale is pretty mind-blowing. The system itself ran, get this, 1,773 experiments. That's over 20,000 GPU hours. And the result? It discovered 106 state-of-the-art linear attention architectures, brand new ones. And here's the real kicker, what they're calling the AlphaGo Moment for this field. It established the first empirical scaling law for scientific discovery, basically proving that research progress itself can now be scaled computationally. Not just by adding more human researchers, more GPUs can literally mean more fundamental breakthroughs. And it revealed these emergent design principles that systematically surpass what humans had come up with.
Wow. Okay. So our mission in this deep dive is to unpack this ASI-ARCH framework. We're going to explore its methodology, highlight these, quite frankly, groundbreaking discoveries, and really dig into what these findings mean, for the future of AI research, and maybe for your role in it too. So let's really talk about this human bottleneck first. I mean, you've probably felt it if you work in this space. AI models get bigger, more powerful, scaling to billions, even trillions of parameters. Yet the big leaps, the architectural breakthroughs, those still seem to depend so much on human ingenuity, right? Teams of really smart people burning the midnight oil for months, maybe longer, just to design one new state-of-the-art model.
It's a very striking contrast, isn't it? AI can process information at this incredible scale, yet the speed of generating and validating new foundational ideas is still limited by, well, us. How quickly human scientists can read papers, brainstorm, code, test, iterate. The paper actually highlights this. They estimate a human-only research process takes maybe 2,000 hours to develop just one high-quality model architecture. Think about that. That's nearly a full year of dedicated work for one design. It's just inherently unscalable when the AI itself is moving at light speed.
And we're not just talking about any minor part of AI development here. Neural architecture is fundamental. It's the cornerstone of the whole AI tech stack. I mean, every major leap we've seen, CNNs for images, transformers for language, those were driven by architectural breakthroughs.
Absolutely. So looking at the big picture now, the key challenge in architecture is boosting computational efficiency without losing expressive power. Historically, designing components or families for this manually is protracted. It takes months of human experts iterating just to get one SOTA architecture. It's a real grind.
Right. And that's why this ASI-ARCH concept feels like such a paradigm shift. It's not just optimizing within search spaces that humans have already defined. That's what traditional NAS mostly does, right? NAS methods are smart, incredibly sophisticated even, but they're essentially picking the best options from building blocks humans already thought of. They optimize inside a known box.
Exactly. What's genuinely exciting, and maybe a bit scary here, is that ASI-ARCH performs what the paper calls automated innovation. It autonomously comes up with truly novel architectural concepts. This really looks like AI's first proper demonstration of genuine scientific superintelligence, specifically in neural architecture design. It's moving from just optimization to actual invention. Like you said, it's building the box, not just finding the best thing inside.
So how does it actually work? How does ASI-ARCH do this? The paper describes it as a closed evolutionary loop, a highly autonomous, tool-centric multi-agent system. Basically, a self-contained AI research lab in software.
Yeah, the structure is quite ingenious. They've set it up with 4 distinct modules, but they're all interconnected, working together. First, there's the researcher agent. Think of this as the creative engine. It's the one proposing novel architectures, drawing on historical data, human papers, and its own previous findings. It's the ideas generator.
Okay, the researcher proposes ideas. Then
Comes the engineer. This agent is the hands-on one. It takes the researcher's designs and actually builds them. It implements the code, it runs the training, and it empirically validates the performance in a real environment. So it's not just theory, it's actually deploying and testing.
Right, theory and practice. What's next?
Next up is the Analyst. This module is absolutely crucial for learning. It takes all the experimental results, synthesizes them, and extracts new insights. It figures out what worked, what didn't, and why. And that analysis feeds back into the system, informing the next evolutionary cycle.
I see. And the last piece.
The final component is the cognition base. Now, this isn't an active agent like the others, it's more like the system's long-term memory. It holds the accumulated knowledge both from historical human research they fed it loads of papers and the AI's own past experiments. The researcher taps into this base. So you have this cycle. Hypothesize, implement, train, analyze, learn, and then back to hypothesize again. This allows for continuous improvement and, this is key, potential self-acceleration.
That makes sense. And how does it decide which architectures are good? How does this evolution actually work?
Well, the way it mirrors natural selection is pretty clever. They developed a comprehensive fitness function. It's not just based on simple quantitative scores like loss or benchmark results, because those can sometimes be gamed by the system, right? Reward hacking.
Ah, right. Finding a loophole in the metric without real improvement. So how do they avoid that?
But their fitness score is a composite. It includes the quantitative stuff, benchmark scores, loft performance, efficiency metrics like FLOPs, plus qualitative assessment.
Qualitative. How does an AI do that?
They use another large language model, an LLM, trained to act as an expert judge. This LLM evaluates things like architectural innovation, structural complexity, implementation correctness, even convergence characteristics, things a human expert would look for. And they do this neat trick with a sigmoid transformation on performance differences. It helps amplify small but meaningful gains and prevents extreme outliers from totally dominating the selection process. It keeps things stable.
Okay, that sounds robust. But training and testing all these architectures must be incredibly resource intensive. How do they manage the cost?
That's a great point. They use a very smart two-stage strategy focused on efficiency.
2 stages.
Yeah. First is the exploration stage. Here, the system casts a wide net. It rapidly identifies promising candidates using smaller models, like maybe 20 million parameters, trained on just 1 billion tokens, and tested on only 500 samples per benchmark. Quick and dirty, relatively speaking.
So find the potential winners quickly without spending too many resources.
Exactly. And then, if a candidate looks good in exploration, it graduates to the verification stage. Here, they get serious. They rigorously validate only the best candidates by scaling them up significantly. We're talking 340 million, maybe 400 million parameters, trained first on 1 billion tokens, then on 15 billion. This ensures the discoveries aren't just flukes at small scale, but are actually robust and perform well in more realistic scenarios.
Okay, let's pull back the curtain a bit more. Inside this AI lab, these agents, let's look closer at the researcher agent. It's the creative one. How does it even start? Where do the ideas come from?
So the researcher maintains this dynamic pool of the top 50 architectures found so far. For each new attempt, it does something interesting. It randomly picks one parent architecture from the current top 10. That's the base it will modify. But then it also samples 4 reference architectures from ranks 11 to 50. These provide like diverse examples or inspiration. So it's building on success, but also keeping diversity in mind.
And how does it avoid just repeating itself or getting stuck in a rut?
That's where dynamic summarization comes in. Instead of just feeding the researcher the same static historical data every time, they use an LLM, a low-temperature one, meaning less random, to summarize relevant prior architecture info on the fly. These summaries are generated fresh each time, introducing subtle variations in how the history is presented. This prevents repetitive prompts and nudges the researcher towards more varied explorations.
That's fascinating. So the context is always slightly different. And critically, this single researcher agent handles both the high-level design motivation and the actual code implementation. Why is that important?
It's crucial for preventing what they call implementation drift. That's where the final code might accidentally deviate from the original design intent, especially if different models or steps handle those different parts. Keeping it in one agent ensures consistency.
Makes sense. Are there guardrails? How does it know if an idea is any good before training?
Oh yeah, definitely. Before any proposed architecture even gets sent for training, it has to pass a 2-stage validation check. First, There's a novelty check using embeddings and another LLM. Basically, is this genuinely new or just a tiny tweak of something we already have? And second, crucial sanity checks at the code level. Does it accidentally introduce ON to complexity? That's a no-go for linear attention. Is causal masking implemented correctly so it's not cheating by looking ahead? If it fails these checks, it's rejected and the researcher gets feedback to try again. It's built-in quality control right at the start.
Okay, so the idea passes muster, then it goes to the engineer agent. This is where, as you said, the rubber meets the road.
Exactly. The engineer operates in a real interactive coding environment. It takes the code, initiates the training process, and importantly, it deals with any problems that come up.
Problems like .code bugs, how does it handle errors? This seems like a major hurdle for automation.
It is, and this is a key differentiator in ASI-ARCH. It has a robust self-revision mechanism. Unlike some previous systems that might just discard a run if it errors out, the engineer agent here is required to debug and fix its own code. It gets the full error logs and iterates, trying to fix the bug until the training can run successfully. This is huge. It means promising architectural ideas aren't thrown away just because of a simple coding mistake. It's like having an autonomous developer who learns from stack traces.
That is a massive leap. Wow, does it monitor the training process too?
Yes, absolutely. There's an automated quality assurance system watching the training logs in real time. If a model's training is, say, 2 or 3 times slower than its peers, suggesting inefficiency, it gets terminated. Or if the loss drops suspiciously low, which might indicate information leakage or some other problem, that run is also stopped. This saves a ton of compute resources and speeds up the whole discovery process dramatically. And remember that qualitative score we talked about. The engineer also uses that LLM as judge to get the qualitative assessment of the final trained architecture, complete with justifications.
Okay, so researcher creates, engineer builds, and debugs. Then we have the analyst agent, the reflective one. What's its role in learning?
The analyst mines the results for insights. It draws on 2 main knowledge sources. First, that cognition base we mentioned. They curated nearly 100 seminal papers on linear attention and used an LLM to extract structured knowledge, the scenario the algorithm used, the historical context. So it taps into existing human expertise.
Right, leveraging the literature. And the second source?
The second is what they call contextual analysis for ablation. This is really cool. The analyst doesn't just look at the current experiment's results in isolation. It looks at the data alongside the results from its parent architecture, the one it was derived from, and its sibling architectures, other designs derived from the same parent. By comparing performance differences across this little family tree, it can infer the specific contributions of different architectural components. It's like doing an automated ablation study. These inferred insights are then archived and fed back into the system to inform future designs by the researcher. It's continuous learning from its own experiments, fully automated.
Okay, the framework makes sense. It sounds incredibly sophisticated. Now let's get to the moment of truth. The results. You mentioned the scale already.
Yeah, the scale is impressive. 1,773 autonomous explorations over 20,000 GPU hours. They filtered this down to about 3,350 promising candidates during that initial exploration stage.
And from those,
an astonishing 106 novel, state-of-the-art linear attention architectures were discovered and confirmed in the rigorous verification stage. And importantly, they've made all of these publicly available on their model gallery.
106 novel SOTA designs. I mean, that's more breakthrough architectures than many human labs might produce in years, maybe a decade. It feels almost unsettlingly efficient.
It really is. And beyond the sheer number, there's the qualitative aspect, what they call the AlphaGo's Move 37 moment. Just like AlphaGo made moves that seemed alien but were incredibly powerful, these AI-discovered architectures demonstrate emergent design principles. They systematically outperform the human design baselines, revealing new ways to build efficient and powerful attention mechanisms. It's like the AI is showing us pathways we hadn't seen.
And this leads to what you said might be the real game changer, the scaling law.
Exactly. This is arguably the most profound contribution, the empirical establishment of a scaling law for scientific discovery itself. They found that the cumulative count of new SOTA architectures discovered scales linearly with the computational hours invested. This is direct evidence that the process of research discovery, at least in this domain, can shift from being limited by human time and cognition to being scalable with compute power. You want more discoveries? Add more GPUs. It's a fundamental shift in how we might think about progress.
Can you give us a flavor of what these AI-discovered architectures actually do? Maybe highlight a couple of those top performers.
Sure. Let's take Pathgate FusionNet. This one introduces a clever hierarchical two-stage router. It helps manage the flow of information for both local and global reasoning, keeps gradients stable, and even has specific gates for different attention heads. It's about smarter information routing.
Okay, smarter routing. What else?
Then there's Content Sharp Router. This one uses content-aware gating, meaning the decision to route information depends on the information itself. And it has a learnable temperature for each head, making the routing more decisive and preventing useful pathways from shutting down too early.
Interesting. Keep going.
Okay, Fusion-gated FurNet. This one does something unique. Instead of one main router, it uses parallel, independent sigmoid gates for local and global paths. This allows both pathways to be active simultaneously. Plus, it adds learnable retention per head to help remember long-range information better.
Parallel paths. Nice.
And HireGateNet, another hierarchical approach. This one uses a two-stage gate, but with dynamic learnable floors. This guarantees that critical pathways, especially the one needed for long-range reasoning, never get completely shut off. Important information always has a way through.
A safety net for information flow. Makes sense. One more.
Right, add a multipath gatenet. This implements a unified gate that combines global signals, per-head preferences, and per-token information for fine-grained control. It also uses techniques like an epsilon floor and an entropy penalty to make sure the different information paths stay diverse and active. These aren't just minor tweaks. They represent genuinely novel ideas and combinations within attention mechanisms, suggesting the AI developed a pretty deep understanding of what works.
Absolutely. So, stepping back, what does all this tell us about AI's ability to design things? How effective was this search, really?
Well, what interesting finding is about the metrics. While that composite fitness score they designed tended to plateau over time, it just got harder to find things that scored significantly higher across all criteria. The raw performance metrics, like benchmark scores and loss, actually continued to show steady, ongoing improvement throughout the process.
So even when the AI's internal target score leveled off, it was still finding objectively better models.
Exactly. Which confirms the system's underlying effectiveness. It kept pushing the performance boundary even when its own complex fitness function made big leaps harder to register. It demonstrates real, continuous progress.
And what about the architectures themselves? Did it just achieve better performance by making the models bigger? That's always a concern.
That's a key question, and the analysis shows quite clearly no. ASI-ARCH achieved these SOTA results without just inflating parameter counts. The model sizes remained remarkably stable, mostly in the 400-600 million parameter range, with some diversification up to 800 million. But no systematic trend towards just getting bigger and bigger. This shows real architectural discipline. The system wasn't just brute forcing with scale, it was finding genuinely smarter designs.
And did it invent completely new building blocks, or did it mostly reuse existing ideas?
It showed a clear preference for established, effective components, things like gating mechanisms and convolutions, which makes sense. But here's a subtle, crucial insight. The very best, the SOTA models it discovered, they exhibited a less pronounced long-tail distribution of component usage compared to the average model explored. Meaning that while the system explored a wide variety of novel components during the broad search phase, the top-performing architectures actually tended to converge on a core set of techniques that were proven to be effective. They didn't rely as much on lots of obscure or brand new components just for the sake of novelty. This kind of mirrors good human scientific practice, right?
Yeah.
Breakthroughs often come from innovative combinations or refinements of established, powerful techniques, not just throwing random new things together. It's focused innovation, not just novelty hunting.
That makes a lot of sense. But you mentioned there was a deeper insight, the real aha moment, about where the good designs came from.
Yes, this is perhaps the most fascinating part of their analysis. They tried to trace the provenance of the design ideas. They categorized them into three channels: cognition, ideas essentially derived from the human expert literature fed into the system. Analysis, patterns and insights identified through the AI's own experiments and ablation studies. And original, completely novel concepts generated by the AI, not directly traceable to literature or its own prior analysis.
Okay, so literature, AI's own analysis, or totally new AI ideas, what was the breakdown?
Well, overall, most ideas still originated from cognition, leveraging our accumulated human knowledge. That's not too surprising. But here's the compelling finding. The top-performing SOTA architectures showed a significantly higher dependency on analysis. About 44.8% of their key ideas came from the AI analyzing its own results, compared to only 37.7% for the other, less successful architectures explored.
Wow. So best results came when the AI was learning more from its own work.
Precisely. It suggests that for AI to achieve truly breakthrough performance, it can't just rehash or recombine past human successes, cognition. It needs to actively engage in its own cycle of experimentation, analysis, and discovery analysis to synthesize novel solutions that are genuinely superior. It needs to learn from its own experiments to truly innovate at the highest level. This isn't just AI processing data anymore, it's AI learning how to discover.
That feels foundational. If we connect that to the bigger picture, it implies a potential shift, doesn't it? From humans primarily feeding ideas to AI towards AI learning from itself and driving its own discoveries, like a self-improving research engine.
Exactly. That's the potential trajectory this research points towards.
So wrapping up this deep dive on ASI-ARCH, it really seems to establish a potential blueprint for self-accelerating AI systems, and it provides strong evidence for the computational scalability of scientific discovery, at least in this domain. The implications feel enormous.
Absolutely. And the authors point towards promising future work. Things like multi-architecture initialization, starting the search not from one parent but from a diverse portfolio of architectures simultaneously. That would be incredibly resource intensive, but could potentially uncover entirely new families of designs.
Yeah.
Also, digging even deeper into the component-wise analysis, really trying to pinpoint the contributions of cognition versus analysis with finer granularity.
And practically speaking, getting these discoveries into the real world.
Right. There's the crucial engineering optimization step. Things like writing custom, highly optimized compute kernels for these newly discovered architectures. That would be needed to make them truly practical and deployable, completing the cycle from autonomous discovery to tangible application.
So this really does leave us with a provocative thought, especially for you, the AI researchers and ML engineers listening. What are the implications of a truly self-accelerating AI research paradigm? How might it change the speed, the very nature of future scientific breakthroughs? And perhaps more personally, how might this fundamentally change your role in the AI discovery process down the line?
Definitely something to ponder as AI continues its journey, delving deeper into not just intelligence, but maybe invention itself.
Thank you for joining us on this deep dive.